my name is Saurabh, and in today's video, we'll explore the principles of overcurrent protection. Friends, in the last video, we covered the basics of overcurrent protection. So, in this video, we'll try to understand what principles we use when applying overcurrent protection to feeders or transmission lines. So, if we talk about the principles of overcurrent protection, there are generally two things involved. The first is time, and the second is current. So, we can divide it into three sections. The first is discrimination by time, which is what we call definite time. The second is discrimination by current, which can also be called instantaneous overcurrent. And the third is discrimination by both time and current. Now, if we look at discrimination by both time and current, we'll see three things. The first is the standard inverse. The second one is the very inverse, and the third one is the extremely inverse. Friends, in this video and future videos, we'll explain all these things very easily with practical examples. First, we'll understand discrimination by time. This is also called definite time. So, friends, just by saying definite time, we understand that we'll set a fixed time in the relay. If a fault occurs in the system, for example, if this is our transformer, or here, our breaker, then if a fault occurs in the system, the relay will observe the time specified in it. And according to that time, it will send a tripping command to the relay breaker. So, what happens in this method? An appropriate time setting is given to each of the releases controlling the circuit breaker in the power system to ensure that the breaker nearest to the fault opens first. So, let's understand this with an example. For example, suppose this is a source, and here, there are breakers B, C, D, E, and their releases. Here, A, there are fuses. We've provided timings for all the relays. For example, B, suppose there's a fuse, and the tripping time is 20 milliseconds. Suppose we've provided 80 milliseconds for the relay on the B side. Suppose we've provided 120 milliseconds for the C side. We've provided 200 milliseconds for the D side. And suppose we've provided 350 milliseconds for the relay on the E side. So, suppose there's a fault here. If there's a fault here, the fault current will go from the source, and this way the fault will flow through the system. So, what will happen now is that the relay will check. Now, all the relays B, C, D, and E, wherever the fault current is flowing, will operate. They will wait for their timing to reach 0, and then send a tripping command to the breaker. You can see that relay B has the shortest timing. So, as soon as relay B reaches 0, it will send a tripping command to the breaker, isolating the fault. Similarly, suppose a fault occurs here. So, if a fault occurs here, the fault current will flow from here, and the timings of relays E and D will activate. As soon as the D side relay reaches 0, they will send a tripping command to the D side breaker. So this is what we call friend discrimination by time. We simply set the timing for the relay here, telling it to wait for its desired time and then send the tripping command to the breaker accordingly. But there are some limitations. What are these limitations? Now, consider that even our relays near the source always have higher fault currents. Suppose a fault occurs here, its fault currents would be approximately 20 kiloamperes. Similarly, if a fault occurs on the B-side relay bus, the fault currents here would be approximately 5 kiloamperes. Why would this be? Because your impedance, line impedance, and transformer impedance are all adding up here. So, what happens now is that even though your fault current is higher on the source side, we're still setting higher timings for the E-side relays, which shouldn't be the case. Even if you suppose the fault occurred here, the relay would still have to wait 350 milliseconds. So, this fault current would continue to flow through the system for 350 milliseconds. So, this is the limitation of discrimination by time. Even the longest fault clearance time for the fault in the section close to the power source. Seconds, we understand discrimination by current. So, we also call this instantaneous overcurrent. So, discrimination by current is realized on the fact that the fault current varies with the position of the fault because of the difference in impedance value between the source and the fault. Let me explain this to you very simply. Suppose this is a single line diagram of a grid. So, again, this is our source. So, as we saw in the time, whatever fault current flows, as we move further away from the source, our fault current level will decrease. Why is it decreasing? Because our line impedance is coming into play, the transformer's impedance is coming into play. Because of this, our fault current is decreasing. We know that current is directly proportional to voltage by impedance. As impedance increases, our current decreases. So, using this fundamental principle, we incorporate discrimination by current into the relay. But friends, there are significant problems here if we incorporate discrimination by current directly. Why? Because even if you can see, the distance between F1 and F2 is very small. Whatever our line impedance is, it will be very low here. So, the fault currents of F1 and F2 here will be similar. The difference won't be much, they'll be between 0.5 and 0.8 kA. Therefore, relays can operate here. Let me explain this with a practical example. Suppose this is a grid system. There's an 11 kilobytes 250 megabytes force installed. Suppose generators are installed. The cables used as transmission lines are 200 meters long. And between these buses, there's also a 200-meter cable. This transformer is 4 MVA, its voltage is 11/3.3 kV, and our percent impedance is 7%. Now here we have taken 4 conditions F1, F2, F3, F4 that if what will be our fault level here, what will be the fault level in F2? How much will it be in F3? And how much will it be in F4? So you can see its calculation that our phase voltage will be 11 kilovolts 3 because ours is an 11 kilovolt system. So the phase voltage of 11 kilovolts 3 will come to 6350.85 volts. Now line impedance at 100 meters. Now you can see that the line impedance at 100 meters given to us is 0.1075 ohm. So this data has been provided to us. So first you find out the source impedance. What will be the source impedance of 11 kilovolts? So we know that source impedance is equal to 11 to the power of 2, that is voltage squared by power. So this will come to our 0.484 ohm. Now let's calculate the transformer's impedance. Because there are transformers installed here, we can calculate the transformer's impedance the same way. 11 squared, that is voltage squared, divided by power, that is 4 millivolts into percentage impedance. Our impedance is 7%, so our transformer's impedance will be 2.175 ohms. Now, you will calculate the fault current. So, suppose there's a fault in our IF1, F1, and the length of our cable is 100 meters. Now, if we calculate it in F1, first of all, our source in voltage is 11 kilovolts, so our phase voltage is 6350.85. So, if there is a fault here, 2 currents will flow. One of our currents will flow from here as well. Another current can flow from our transformer as well. So, first of all, we are doing 1 by parallel. So 1 over 0.484, that is our source impedance. Now plus 0.01075, that is our cable impedance. You can see that the cable's impedance is 100 meters. 0.01075. So this is our plus the transformer's impedance coming in parallel. So 1/2.1175, which is our transformer's impedance. Now if we calculate this, friend, then it will come to 15.83 kilometers. So this is our fault current, that is if there is a fault in F1. Here if the fault occurs 100 meters away from the source, then if there is a fault, then maximum 15.83 kilometers fault current will flow. Now we will calculate F2. If our fault occurs in F2, that is 100 meter plus 100 meter plus 100 meter, that is 300 meter. From here the cable length of F2 from the source is 300 meter. 100,000, 100 plus 100. So now we will calculate our voltage by impedance from the same way. This is the impedance. Our final impedance will be 1 over 0.484, that is, the impedance of the source, plus 3 asterisk 100 meter, which is 0.01075. Plus the impedance of our transformer. So this will come to 15.30 kilo ampere. If we calculate F3 from the same way, then our current will come to 15.05 kilo ampere. And if we calculate F4, that is, the fault wave on the right side of the transformer, that is, what will be our fault current after the transformer? So if you see here, then the same way 6350.85 is our phase voltage plus 0.484 is our source impedance, then 0.1075 asterisk 4, that is your 200 meter. 200 meter becomes 400 meter plus our transformer's impedance. Now if there are some source buses on the LV side, we will also fit that. Then one by one the transformer's impedance plus our 100 meter here. From here to here we took that impedance 0.01075. So if we calculate this, then the fault current IF4 will come out to be 5.38 kilo ampere. Now the thing to understand in this is that if we look at F2 and F3, then the fault current of F2 is 15.30 kilo ampere. The fault current of our F2 is 15.30 kilo ampere and the fault current of F3 is 15.05 kilo ampere. So, there's not much difference. You can see here that there's a difference of around 0.3 kilo amperes. So, even if a fault occurs in F2, the relay can send a tripping command to the breaker in F1. And if a fault occurs in F1, the relay can also send a tripping command to the breaker in F2. This increases the chances of malfunction. So, that's why discrimination by current is used. It's practically impossible to use in any system, because the chances of malfunction increase significantly. So, I hope you've read about discrimination by current and discrimination by time. The reason for explaining these two methods is that we'll use these two methods to solve all the numerical problems going forward. And it's using these two methods that we'll now study, discrimination by both time and current, or IDMT. This will make it easier for us to understand. The next method, which is used for 99% of overcurrent protection, is discrimination by both time and current. We've seen the time and current limitations. However, if we use both in these cases, all our problems will be solved. Let's try to understand how they will be solved. This is also called IDM, which is the inverse of definite minimum time. So, if the current is high, as we just saw here, if the source has high current, then the timing should be low. Because we're fitting a high current system, what does this mean? If our current is high, then this is our time. So, if our current is high, then our time should be low. And if our current is low, then our time should be high. That is, both should be inversely proportional. You can see here that if my current is higher, then my timing is lower. If my current is lower, then my timing, the relay operating time, is higher. So, if we use this method, we can say that we have made the system operate properly. We are seeing that if a large current is flowing in the system, it should be isolated as quickly as possible. If a small current is flowing, we can add a slightly longer time delay. In this also, as we looked at IDMT, graphs are created in 4 ways. The first one is the standard inverse. The second one is the very inverse. The third one is the extreme inverse, and the fourth one is the long time inverse. So, these are the formulas for all of them. If you look at the standard inverse, TMS means time multiplier setting 0.14. IR to the power 0.02 to 1. So what is IR? That IR is the plug setting multiplier. We also call it PSM. Plug setting multiplier. We will try to understand what TMS and PSM are. If we don't understand this, we won't be able to understand overcurrent protection. So IR is the plug setting multiplier. So you can see this graph on the right side. That is your time by plug setting multiplier graph. So plug setting multiplier and time multiplier setting are our electromagnetic relays. Plug setting multiplier is nothing but the ratio between fault current and the pickup current. So, whatever your city's pickup current is, how many times your fault current is, that is what we call the plug setting multiplier. So you can see here that graphs of your standard inverse, very inverse, extremely inverse, and long time inverse are given here. So friends, in the next video, we'll try to understand how we draw these graphs using the plug setting multiplier and the time multiplier setting. Second, if we look at a practical system, for example, in a switch yard with many feeders, transformers, and generators, how do we do that if we need to set relays there? What factors should we consider when setting relays? And finally, we'll see when we use standard inverse, when we use very inverse, or when we use extremely inverse in a system. For example, we use extreme inverse mainly where source side relays are located or where transformers are installed. We will try to understand practically why we use this word. So friends, that's all about this video. If you like the video, please like, share, and subscribe. If you have any doubts, you can ask in the comments section. Thank you.